so let us get started. Welcome back. Happy Friday. Here's our look at the calendar. We just took test number 2. Given the tests all back, the median grade was 79. That means half of you did better than 79, half of you did lower than 79. High grade was a 99. I will say that I was pleased with the results. This is a solid effort, generally speaking. Some people obviously didn't do that great. Some people did awesome. So I'm just kind of talking in generalities right now. But I think that this was a fair test on challenging material. So I'm feeling pretty good about the overall results. If you'd like to talk about your specific results, I'm free right after class today, or pretty much right after class any day. We can chat about where I think you are right now if you're interested. Okay, so here's our look at the calendar. Today we start packet number 3. It's on your table. Go ahead and grab one. This is the very last packet for the entire semester. Brand new topic that we're getting into here today is sequences, and then for like the next 8 classes or something, it's all about series, whatever those things are. We'll have test number 3. Then we've got 3 days of new material before our review for the final exam. This is the first day that the final exam has fit on this smartboard screen while we're looking at the calendar. So we are definitely getting down to it, okay? No projects outstanding right now, but on Monday I will give you project number 7. Any questions on the calendar? Okay, then we start here on page 2. In this class, we introduce the concept of sequences. Today, we leave integrals and move on to a new topic for the next 4 weeks. We've been working with continuous phenomena, things that happen all the time, for example, water flowing over a dam. For the next few weeks, we will focus instead on discrete phenomena, meaning phenomena occurring at distinct moments in time, to really drive home the difference between this continuous and discrete business. For the economics applications that we did recently, we had our first example talking about a basketball player who got a signing bonus, and then he got a salary at the end of 1 year, 2 years, and 3 years, right? How many times did he get paid? 4 times. That is discrete, distinct, countable 4 times, as opposed to the tutoring business we talked about, where we had this formula, something like 400 t plus 1 squared. You guys remember that example? And it said money is coming in at this many dollars per year. And we weren't imagining getting paid $1,800 just once at the end of the first year. We were imagining that $1,800 coming in little fractions of pennies at every moment of the day. That is a continuous phenomenon, okay? So we've been doing continuous the whole semester. For the next bunch of weeks, we're going to talk about discrete stuff, distinct moments in time. Okay, lots of vocabulary and notation at the start. Stay in the habit of using correct calculus notation. What is a sequence? Here's our first example, 1, 3, 5, 7, 9, etc. That is a sequence. It is just an infinite ordered list, right? Infinite ordered list, that's all. We could also think of the sequence as being a function whose domain is the positive integers. So here's our sequence down here, 1, 3, 5, 7, 9, etc. Here are the positive integers, 1, 2, 3, 4, 5, 6. And we can just say that 1 gets mapped to 1, and 2 gets mapped to 3, and 3 gets mapped to 5, and it's just a function. So for example, s of 2 is 3, right? F is like our standard function notation. We'll use s for sequence. S of 2 gets mapped to 3. More common than the function notation is to use subscript notation, where the little subscript is just asking you which numbered term in the sequence are we referencing. So let's try a couple of examples here. S of 7. It's asking us for the 7th term in this list. We are currently looking at the 5th term right here. What is the 7th term? 13. Everybody okay? Right. So this equals 13. Go ahead and write that. S sub 100 equals. This is our subscript notation. It is just asking us for the 100th term in this list. That is all. Okay, clearly we don't want to count them all out. So we're looking for a nicer relationship here. Some of us have already figured it out. A relationship where we can look vertically. What can I do to this number to turn it into this number? One thing you can do is add 3. But adding 3 is not the consistent rule, right? So we want a consistent rule. What can you do with 4 to turn it into 7? Double it and then subtract 1, right? Does that rule work with 3 into 5? Double it to 6, subtract 1. Great. I'm convinced. So double and subtract 1. How much is S sub 100? 199, right? Just double and subtract 1. And then finally, Sn is asking us for the nth term, the general term. So I'm placed down on this list. And again, we just use Tala's idea here. It's double and subtract 1. So what is it in this case? We'll write 2n minus 1. Right? Double and then subtract 1. Okay, a little vocabulary. S sub 1 is called the first term. S sub 2 is the second term. S sub n is the general term. That's it. Easy peasy. Okay, a sequence. Remember, sequence is just this ordered list going forever. 1, 3, 5, 7, 9, forever. We can say that that single sequence either converges or diverges. This is going to be tricky because we've already seen these two words with respect to improper integrals. When an improper integral converged, it meant that the area was finite, right? We approached a single finite number. To say the integral diverged meant that the area was infinite. So it's the same idea here. If that list of numbers, 1, 3, 5, 7, 9, is approaching a single finite number at the end of the day, then we say that the sequence converges. But if it is approaching infinity, or it is not approaching a single finite number, then we're going to say the thing diverges. 1, 3, 5, 7, 9. Does it approach a single finite number? No. Blows up to infinity. That sequence diverges. Good? Let's talk about a couple of other sequences here together. S sub n equals n over n squared plus 4. Before we talk generally what this thing is doing at the end of the day, let's just find the first few terms together. S sub 1 just means change all of those n's into 1s. What do we get here? 1/5 is good. Don't say it out loud, but can you guys write down S2 and S3 for me? Okay, S2 before we reduce is 2/8, and then we'll reduce that to 1/4. And then S3, 3/13, right? Don't forget to add that 4 there, 3/13. Okay, so this is the start, the first 3 terms of another sequence. And the question is, what is the limit of that sequence as n goes to infinity? That's what we're talking about at the far right. That's how we think about convergence or divergence. So let's just use our limit notation. I'll copy that rule. We know that for end behavior, we're going out to infinity. The only thing that matters is leading term on top and leading term on the bottom. So we can ignore this plus 4, right? And then that guy reduces to just 1 over n. And when n is really big, what does that approach? Which is 0. So if you look farther and farther into this sequence, you get terms that are getting closer and closer to 0. Do we say that sequence converges or diverges? Converges. Any finite number, we say the sequence converges. So this one converges to 0. Sn converges to 0. Any finite number. Questions on that? Okay, next example, 1.2 to the n. Again, let's write out the first few terms here. Okay, first one, 1.2 to the first, it's just 1.2. Next one is 1.2 to the 2, 1.44. I think 1.728, am I right on that one? Yes or no? Yes? Okay. And then we ask the same question. What's happening at the end of the day? As n approaches infinity, what happens to this thing? 1.2 to the larger and larger power goes to infinity. How come? What are we? Yeah. Is this an exponential growth or decay? Isn't it? It's like f of x is 1.2 to the x. Is an exponential growth function because that 1.2 is just a little bigger than 1. 1 is our magic cutoff, right? If it had been like 0.9 to the x, that would be an exponential decay. So this one's exponential growth. So that means that this guy goes to infinity, which means that this sequence does what? Yeah. So in this case, Sn diverges. Questions on that one? Okay, so when we're ready, next page. Okay, turns out that we can show that a sequence converges if we know that it is bounded and monotone. Let's make sure we're clear on these two words here. Bounded means trapped by a finite number. Really means trapped between two finite numbers, but trapped by a finite number. If I know for sure it doesn't go to infinity, and I also know for sure the sequence is monotone, which means always increasing or always decreasing. If we know bounded and monotone, we can say for sure the sequence converges. So let's be clear. Suppose that I'm standing on the real number line right here. And I'm just going to walk along this real number line according to the definition of one of the terms of our sequence, okay? So for example, what was the first term of the first sequence we just did? The n over n squared plus 4 was 1/5. So I'm standing here at 0. Positives are over here to the right. So I'm just going to walk over here to 1/5. What was the next term? It was 1/4. 1/5 and 1/4. Which way are we going? 1/4 is slightly bigger, right? All right, what was the next one? What is it? 3/13. Let's see, 3/12 would be a quarter, so 3/13 is a little bit less. So now I'm going slightly back this way, right? All right, now suppose that I say for sure that I'm decreasing the rest of the time. That means always walking left. Every step I'm going to walk to the left. And suppose that we can also look at that and say, well, it's never negative. Agree? That n over n squared plus 9. There's nothing in there that could possibly make it a negative. So if I tell you that I am always walking to the left, but I'm never getting past this 0 number, can you say for sure that I have to converge to a single number? There's no way I can make it to minus infinity, right? Because I'm never allowed to cross here. And there's no way I can make it to plus infinity because I'm trapped here between 0 and 1, for example. And there's no way for me to like oscillate back and forth between two numbers because I'm always walking to the left. For sure, we are going to converge. We're going to hone in on a single number. Can't say for sure that it's going to be 0, but we're definitely going to hone in on a single number. There's no other possibility, right? And so that's what this theorem is saying. So for example, the sequence here, 0.19, that's the first term. 0.1919, that's the second term. 0.191919, that's the third term. That sequence right there, I want to know whether it converges or diverges. Well, is it bounded? Give me a number that's for sure bigger than all of these guys. All of them forever. How much? 0.2. You guys are pretty stingy with your bound. 7 is also an okay bound. Right? But definitely it is never bigger than 0.2. I agree. And is it always increasing? Every term is just a little bit bigger than the previous one. So we can say monotone increasing in this case. And these two things together tell me definitely that sequence converges or diverges. That sequence converges. It hones in on a single finite number. I don't know what it is yet. Talk about what it is next class, but it converges for sure. Don't read too much into this theorem. It doesn't mean that the only sequences that converge are the ones that are bounded and monotone. There are other sequences that can converge that are not bounded. Sorry, it's got to be bounded. But there are sequences that can converge even if they're not always increasing or always decreasing. So don't read too much. This is just one way a sequence can converge, but there are others. Okay, so the activities on the next page, I actually just want to start briefly with this little thing together, even though it's part of the activities. Quick detour into the algebra of factorials, and then you'll practice. So the factorial business is going to help in a coming class, but we're just throwing it here because we have time today to talk about this factorial business. So what we're going to do is simplify some factorials. It's going to be really common for us to have to simplify division with factorials, and factorials is something we have limited experience with probably. So we'll just take a little break here and talk about simplifying. 12 factorial over 10 factorial. So remember, well, this is written out here. 12 factorial just really means 12 times 11 times 10 times 9, all the way down to 3, 2, and 1, right? 10 factorial means the same thing from 10 down to 1. And even without doing all of that calculation, we can see there's a lot that simplifies. What cancels on the top and the bottom? Starting from what cancels? The 10, right? 10 all the way down to 1 is exactly the same as 10 all the way down to 1. And so this problem, that fraction reduces really simply to just 12 times 11, right? 132. Easy peasy. Okay, this next one is tougher. But let's see if we can do it. This is written out, but I'm going to write it out again here. So maybe don't look at all that typed up stuff. 3 n plus 2 factorial over 3 parentheses n plus 1 plus 2 factorial. Both of those guys squared. I promise this was not just made up to torture you. Like, we're actually going to have to simplify things that look exactly like that real soon. So let's do the algebra piece today. Okay, first thing I'm going to do. You guys can write this down too. 3n plus 2 factorial squared. We're just copying that guy. Divided by, and then I'm going to distribute in the parentheses here in the bottom and combine like terms as well. So the 3 distributes, makes 3n plus 3. Add the 2. I have a 3n plus 5. Yes? Okay. So the main idea here to simplify is to write out enough factors of the bigger one until it catches up to the smaller one. Top or bottom, which one's bigger? Bottom is bigger. That 3n plus 5 is more than the 3n plus 2. So I'm going to copy the top for the last time. And then we're going to write out a few of the factors of the bottom. 3n plus 5 factorial literally means you are taking 3n plus 5 and you are multiplying it by the next number that's one smaller. What is one smaller than 3n plus 5? It's 3n plus 4. Everybody see it? 3n is just a distraction. Plus 5. Next term is going to be a plus 4. What's the next one? 3n plus 3. What's the next one? 3n plus 2. I'm going to stop right there. What I've written up here is a lie currently, because you don't get to just stop at 3n plus 2. But there is one little symbol that I can put in here that is going to make it the truth. What can I put to make this the truth, equal to the previous statement? You could put some dots. That's 3 symbols, oh, 1 symbol. I can put an exclamation point right there. The exclamation point is only on the 3n plus 2. And isn't that what the dots means? Is just keep going, but start with 3n plus 2. And the reason I like stopping it right there is that now it is a copy of the thing that is sitting upstairs. You see it? And so the 3n plus 2 factorial upstairs completely cancels the 3n plus 2 factorial downstairs. From that point onwards, they cancel. So all that's going to be left is the stuff in the front. So this guy and this guy completely disappear. The only thing I've not been careful about so far is the fact that there have been squares everywhere. Well, the 3n plus 2 factorials were both squared, so they both really cancel. The only thing I need to make sure I do is square everything that's left over. Okay, what number am I putting on the top? 1. Everything canceled. Got to introduce the 1. I've got a 3n plus 5. It is inside of a square. Let's go ahead and deal with that now. It's squared. I've got a 3n plus 4. It is squared. And a 3n plus 3. And it is squared. And everything else disappears. Okay, so again, the idea with canceling factorials is you write out enough terms, enough factors of the bigger one until it catches up to the smaller one. Make sense? Okay, so the activity is lengthy today, so you're going to really try to motor. Do these 2 examples with factorials first, and then you'll do a bunch of sequence stuff starting on the next page.